is in plasticity. Right? We have in plasticity, so in elasticity, we have this, right? Stress strain curve, it looks like that. We don't even need to use Newton's method because the stiffness matrix is a constant. Right? It's a set of constants. But in plasticity, we have some nonlinear behavior, right? And so the stiffness matrix is really, it's the reason it's called the tangent stiffness is it's literally sort of what's at any point in strain along the loading path, we need to define this point, this line that's tangent to the curve. And in order for us to preserve the quadratic convergence properties of Newton's method, when we define this tangent, it has to be consistent with the return algorithm in our plasticity model, right? So if you remember in J2 plasticity, if we look down the hydrostat, we have some yield surface, and the state of stress can either be one of two places, right? It can be inside, in which case the material is elastic, or it can be on the surface, in which case the material is plastic. The surface can evolve, can grow, can shrink, but the state of stress always has to be on it. Okay. So when we find ourselves outside of it, so when we take a trial step and we find ourselves outside of it, and so what a trial step is an elastic step, right? I mean, we don't know if the material is plastic or not. The only thing we can do is take a step forward. And when I say step, I really mean time step, but time could be fictitious. In other words, sometimes we solve quasi-static problems, nonlinear quasi-static problems. So really we're just solving this equation, right? So there's no time derivatives, right? This is quasi-static, okay? But we either through kinematic boundary conditions in U, we're fixing the displacements, or through incrementing the load in F, we'll have to do that in increments. And the reason is, in a nonlinear problem, right? In a linear problem, the stress is just going to move straight up along that line, right? So it doesn't matter how much I strain it in one step, I can predict where the stress is going to be, right? But in a nonlinear problem, if I take a huge step in the strain, right? So if I just go from starting at no load and I take one giant step and strain it this much, all I have is the two endpoints. My tangent stiffness is going to be that, which is not representative of the loading path of material, and it's not going to converge. Okay. So what we'll do a lot of times, and you may hear me say load step or time step, okay, but that time can be fictitious. Okay. So all that means is I'm going to take, if I'm going from, if I've got a piece of material and I'm going to take it from 0 displacement to 10, whatever, 10 meters, 10 whatever, 10 millimeters. I would, in a nonlinear problem, I would often increment that and go in load steps or increments of 1, maybe, or half, or something, right? So I'm going to take, instead of going straight from 0 to 10, I'm going to go from 0 to 1 to 2 to 3 to 4 to 5 in increments. And at each load step, I'm going to run it through the Newton iteration and let it converge, right? And that's going to give me first it's going to allow it to converge, because if you take one giant step like that, it's never going to converge, right? Because the tangent is not consistent with the response of the material, all right? So the point I was going to make about the plasticity model is, right, if we don't know what else to do, we take an elastic step, and then we evaluate the stress. Specifically, if we're talking about J2 plasticity, like my drawing is there, we evaluate the deviatoric stress. We compare that to our yield functional, and we decide Are we inside? If we're inside, we're elastic. We just accept that step and move forward. If we're outside, we have to get ourselves back onto the yield surface. And we do that, remember this distance was something like delta lambda, right? So this is sort of an increment of plastic strain that's going to return us back to the yield surface. But how we choose to get ourselves back on there, specifically, if the yield surface is a function of, say, strain rate. So remember, if you have a dynamic problem, you might have a constitutive model in which the yield surface is going to grow as a function of rate. And in that case, we have to discretize the strain rate in some way over the load steps. And we have choices of how we do that. You can use a fully explicit, fully implicit, a mixed method. So we actually have a local Newton iteration just in this step of getting us back onto the yield surface. And our choice, and I'll write some equations down here in a second, but our choice in how we decide to return ourselves to the yield surface affects the overall tangent stiffness. And so the tangent stiffness has to be consistent with the algorithm that we use to get ourselves on the yield surface. And if you do that right, you can maintain the quadratic convergence properties of the method. If you do it wrong, if you do it wrong, it doesn't necessarily mean, or if you use the continuum, like if you don't take into fact that there's that you discretize and you have a local Newton iteration right here, if you just derive the continuum tangent stiffness, it doesn't mean you won't converge, because you might be approximately have the right slope. It's just going to lose the quadratic convergence properties. So you're not going to get there in 4 steps or whatever. Boom, boom, boom. You're not going to cut it down that fast. So part of what I'm going to write here is sort of a rehash from our notes on 923 and 925. So if anything's not familiar to you, you can go back and look at those notes or watch those videos again. So if you remember, we derived this very sort of generic and systematic way for solving for an increment of plastic strain. We used the deviatoric total strain rate times Q, which Q is the direction, right? Q is the direction here. Q ij is Sij over Sij, Sij, right? So Q is the direction, plus S dot, where S is what's underneath here, right? The Sij, Sij. Over 2 mu minus lambda dot. Right, so we derive that, but this is all we haven't introduced any discretization yet, right? Discretization in time, because these are rates, okay? And this is why, even in we write this in rates, and this is why we have to have steps. We have to have load steps. It doesn't make sense if we have rates here. It doesn't make sense to not have an increment of time, even if time is fictitious, right? So if we use a fully kind of a Euler, well, we won't decide yet, but we're going to say that the total strain rate is the increment between n plus 1 and n over delta t Qij plus delta S over delta t 1 over 2 mu delta lambda over delta t. That's equal to 0. And of course, the delta t's all cancel, so it doesn't even matter that time is fictitious here. So then, from that equation, we can say that increment of deviatoric strain, Qij, plus delta lambda equals 0. So remember, this increment of strain it's a strain-driven problem. So this comes from the boundary conditions, right? I mean, this comes from I'm applying a force or I'm applying a displacement, and therefore, I compute an increment of strain because of that. Right? So this is sort of an input to this equation. So it comes about because of the boundary conditions. Right? So here we know, Sn is known, right? This is the magnitude of the deviatoric stress from the previous time step. Right? The Sn plus 1 is the square root of 2/3 y n plus 1. Right? And if you remember that all comes about because of this. The square root of 2/3 comes about because in a uniaxial yield strength test, the stress looks like that. Therefore, S is square root of 2/3 minus 1/3 y minus 1/3 y. And if you take the magnitude of that, then you get the square root of 2/3 y. So y, in general, might be a function of many internal state variables. In this case, we'll just assume that it's a function of the equivalent plastic strain and the equivalent plastic strain rate. Right? Well, we know that the equivalent plastic strain rate is square root of 2/3 delta lambda, or actually square root of 2/3 lambda dot. I haven't discretized anything yet. Okay. So then y at n plus 1 is equal to y, and we have a choice here, right? We could use, say, the old value of equivalent plastic strain and square root 2/3 delta lambda over delta t, or we could use, I should put an n here. So we could use the old value of equivalent plastic strain and plug it in. That would be like an explicit method, right? So the new yield surface is a function of the old equivalent plastic strain and the equivalent plastic strain rate, which is a function of delta lambda, which is what we're solving for. Right? But we could also use the current value of equivalent plastic strain which is an unknown, but it's also a function of, right? So we could write the current value of equivalent plastic strain as the old value plus the rate. Times delta t, right? In other words, if we write in a continuum way, so if I can say that the new value of equivalent plastic strain is equal to the old value of equivalent plastic strain plus the strain rate times delta t, right? Where then the strain rate is delta sigma over delta t, so the delta t's cancel. But But delta sigma, of course, these are all plastic strains. Right? The delta sigma p is equal to minus 2/3 delta lambda. So the strain rate is still there. Equivalent plastic strain rate. So now I have my whole yield surface is a function of things I know and delta lambdas, which I solve for, right? So then if I were to plug all that back into our equation, so now this equation, of course, this y would be some function, right? Some function of, to give you an example of one for viscoplasticity, might be that it's like that'd be an example of a model that would model viscoplasticity. So this would be your quasi-static yield stress, and then you'd have an increase due to work hardening. This is due to plastic strain evolution, and then some fitting parameter, and this is also a fitting parameter, a normalization parameter. Okay, so basically this would be this would be the strain rate at which you measure that, right? So quasi-static, right? I mean, there's always some rate, right? So this would be, so this would be the rate at which you measure that, the reference strain rate at which you measure that. But yeah, and ultimately these are sort of like fitting parameters, as are N and M. So this would have the quasi-static yield stress plus an increase, a power law increase due to work hardening, and a power law increase due to strain rate hardening, viscoplasticity. If I load it faster, material gets stronger. It also work hardens, so as I strain it more, it gets stronger. Right? So then you just, everywhere you see an EP, you'd plug in this, and everywhere you see an E dot P, you'd plug in this, and then you just have one big ugly equation for delta lambda, but you can use a local, but it's just a 1D equation, right? So here you just use your regular old Newton's method, straight up Newton's method to find it. Right? Find what delta lambda is. Okay. And then, ultimately we're solving, well, we're going to update the constitutive model in rate form. So we'd have the generalized Hooke's law that looks like that. So then when we discretize this, we have that. So we need to know what the new stress is according to the stress update, right? And so we had that the magnitude of the deviatoric stress at n plus 1 is equal to the trial stress if that's true, and the square root of 2/3 yn plus 1 q trial if that's true. So then, go back over here, we just update the stress is this stress plus the pressure, where the pressure at n plus 1 is the old pressure plus the bulk modulus times the hydrostatic strain rate times delta T. So this is for pure elasticity. Right? We're not talking about poor elasticity here. So, look, I'm missing a page. I'm missing a page. But, so our tangent stiffness has to be consistent with this whole algorithm. Right? And to derive it means you have to sort of run the derivatives via change.